record. Here we go. All right. So your test. Test 1 is returned. Please pick it up. I don't want them. I want you to have them. You have to hang on to them forever, or don't. I don't care. No one's gonna ask me, what was the average? And then I say, that's the wrong question. But no one asked me, so I guess I don't get to say that. What should we really be asking? What was the shape of the distribution? It was normal. Fine, what was the average? 68%. So it wasn't very high. I will take this moment to remind you that as long as your final exam is better, right, then I'll move the weight of one of your tests to the final exam. So pressure is kind of off, can move forward, you can redeem yourself on the final exam. So as long as you're improving, I'm happy. Okay. I'll post the solutions, but I just finished tallying. Don't worry, I have the scores on my laptop, but I haven't posted them on Moodle yet even. So I had a test in my last class. So I was frantically finishing. I gotta get these back today, so I don't have to hang on to them anymore. So I'll post those and have a look at the solutions. There are two different versions. We're in such a tight room, obviously. And so there will be 2 sets of solutions, but it'll say on the top if you were version 1 or version 2. They're the same, just different numbers. Okay. Good. How about some review from last day? We started talking about sampling distributions. We introduced the idea of the central limit theorem. So the CLT, the central limit theorem, which says that the distribution of, we start with sample proportions, right? We say that the distribution of sample proportions, and I'll do little kind of annotations here. A sample proportion P hat follows a normal distribution with a mean of P, mu is P, and a standard error or a spread of PQ over N square rooted. Standard error of P hat is the square root of PQ over N. We introduced this idea of the standard error. Oh, whoops. Wait. Let me just mute everyone because I always forget. There we go. Okay. Unless that was a real question, sorry. But it kind of sounded like just proportion, so maybe it was. I'll never know. Muted them all. All right, so this idea of the standard error is because the standard deviation is for a single observation, right? Whereas the standard error is for the distribution of a statistic. So here, I'll just make a note. The standard deviation is the spread for a single observation versus the standard error is the spread for a statistic such as p hat. Right, a statistic is a measurement from a sample. Yeah, it's kind of a grouping. So we have the standard error of p hat, and this is a little subscript p hat, because later we're going to have other standard errors, and it's nice to just indicate which standard error this is for. This is the only standard error that we have so far, and so you can drop the p hat, the subscript p hat if it's confusing to you. If you don't like it, that's totally fine. I'm going to put it on there just because then if you're going through, then maybe it'll help it make sense. But the standard error of p hat is pq over n all square rooted. So if the standard error is the spread, right, then as I increase my n, right, if I increase my sample size, then we can kind of go through the domino effect. If I increase my n and then I'm dividing by a bigger number, which means overall this thing is going to decrease, right? It's going to get smaller. If you take the square root of a smaller number, it's still smaller, right? And so here, I'll also highlight where q is 1 minus p, because I'm lazy. I don't feel like writing it. Right. Okay. So we said as n increases, the standard error of p hat decreases. In kind of our work, right? So this is the theoretical standard error. Right? What happens is, okay, P, remember, is the population proportion. We don't know the population proportion. And so in practice, we don't know P with the population proportion. Right? In fact, we're trying to figure out what it is. Yeah. We are trying to figure out what it is. That becomes a problem though, because the standard error uses this P, right? And so what do? We use our best guess at what P might be. Yeah. So in our work, in our calculations, let's say, in our calculations, we use P hat instead, which is our point estimate, kind of introducing that terminology as well, or reviewing our point estimate of P, our best guess at what P might be. All right, I took a sample, and as long as my sample size is large enough, right, then I can use the normal distribution and I can find the standard error. And what I can do is I can use the p hat instead of my p's. And so for confidence intervals, which we introduced last day as well, confidence intervals, we have some conditions that we need to check. And what we said was, okay, these are kind of long. And so, but they'll always check out it's just going to be a matter of kind of knowing what to check. Okay. And so usually how I have this on a test is I just give you a bunch of options and then you check the ones that are appropriate, because I don't want you to have to memorize it for just 1 mark. There's a lot of memorization for not very many marks. And so that's why I kind of like to give you something to go off of. But the conditions for confidence intervals, I'll highlight this because it's going to be important. The first one is the independence condition. Oops. Independence is if we have a random sample, we can assume that we have independence within our sample, right? Now we talked about, okay, what if it doesn't say explicitly that the sample was randomly selected? Then we have to assume that it was randomly selected, right? So then we state that that's something that we're assuming happened, right? And so feels weird in the beginning, but those are the conditions. And so we need to either have it stated explicitly or say that that's something we're assuming. The n less than 10% condition, our sample size has to be less than 10% of the population. Yeah. Otherwise, we've captured too much of the population. And then when you've gathered too much of the group that you're interested in, then you're introducing siblings and married couples and things like that. And especially for opinions, for opinion sampling, then you want to avoid that, right? You want all these opinions to be independent of each other. And so that's the idea. So we're checking, is my sample size large enough? And then, but not too large. Kind of weird. The second condition, or the second part of the condition, is the normality condition, or the sample size condition, if you prefer. I'm gonna add a page here. I'll put this on the next page, otherwise it gets weird. So what we're gonna say is we need to have at least 10 observed successes and at least 10 observed failures. Yeah. And so n times p hat, which is equal to x, we introduce this capital X as the number of successes. Has to be greater than or equal to 10. Yeah. This is at least 10 observed successes. N times q hat, which is also n minus x. And I'm doing both because you might have different pieces of information. Has to be greater than 10, which means at least 10 observed failures. I'm going to highlight the observed because this, we need the observed successes and failures for confidence intervals. I don't know if we'll get to this point in hypothesis testing today. I think so. But what we'll see is we have the same conditions for hypothesis testing, except we'll need the at least 10 expected successes and at least 10 expected failures. So it's going to change just ever so slightly, but we can handle it. So that's why I'm highlighting it here. Even though we haven't seen it yet, this will change for a hypothesis test. But the other conditions, these two, little guys here, they stay the same. Yeah. Now let's see. What else did we talk about? So if the conditions are met, so that's the end of the conditions. If the conditions are met, then if the conditions are met, I'll even say they will be. So it's not a matter of, you know, oh no, this didn't pass. They will always pass because I'll make sure of it. Okay. Then we can proceed with making our confidence interval. Then we can proceed with the confidence interval. From our formula sheet, I'll grab it so you can see. Oops, hey. From our formula sheet, we have this. P hat, we know is a sample proportion. Z star, that looks familiar. We've seen it on our tables, which I forgot to bring again, but I was so proud of myself for bringing the tests that I think I'm off the hook. And so Z star is on our table, right? And that's the only thing that dictates the width of our interval, right? And then the square root of P hat Q hat over N, right? Because here, this is the standard error. This is the standard error of P hat, where we've just replaced the P's with P hats, right? And therefore Q's with Q hats. One thing we didn't talk about that I'm going to introduce now, just hold tight, is that this whole plus minus chunk is called the margin of error. We talked about the margin of error, but we didn't name this chunk the margin of error. But now you know. So you've got the standard error, but when you multiply it by your Z, which determines the width of your interval, then that is your margin of error. Z star is from the table. So really, all you need to build a confidence interval is your P hat, your sample proportion, right? And then your Z star, you need to know what confidence interval to build. I will always phrase the question as construct a 90% confidence interval or construct a 95% confidence interval, 99%, whatever. I'll always give you the percentage. And so that's where you're gonna know what Z star to use, right? Let's grab it. Copy. Paste. So here, your confidence level is up here, and then you're going to trace down to whatever Z star that you need. So if you're building a 90% confidence interval, then your Z star is 1.645, for example. Right? So you just ignore all this middle junk. I cut it out. 95% confidence interval, we use 1.96. We know from the 68, 95, 99.7 rule that's approximately 2 standard errors now, right, from the center. And that's the exact same procedure that we're using here. It's just that now we're talking about P hats, the distribution of P hats. We use 1.96. I want you to use the values from the table just because they're slightly more precise. And that's what I want. So from the table down here. Yeah. And then we did a lot last day. Holy smokes. Then what did we say? Okay, building the confidence interval, not a big deal, right? Kind of the math is fine. Once you have your p hat plus minus your z star times the square root of p hat q hat over n, you're going to get some lower bound, right? Which is your p hat minus that margin of error, right? Up to some upper bound. You're going to write them like this, whatever the lower value is, comma, the upper value. I don't want to see those switched around. Very common though, because we have the plus and then the minus. And so it's tempting to do the plus first and then the minus, but you want to go down first and then up, and then round brackets around it. Yeah. That's only half our work though, right? Building this confidence interval, then we have to interpret the confidence interval. And I gave you a canned interpretation to use. Interpret the interval. And on test 2, it's going to be a lot of confidence intervals, a lot of hypothesis testing, but that's all we're doing. Get to do it over and over and over again for a bunch of different types of questions. Okay. And so half of your marks for the confidence intervals will be your interpretation. So you don't want to forget that, and you have to commit it to memory probably. Unless you've already memorized it, but feels unlikely yet. You will. Okay. The canned interpretation that I want you to use is this. We are some percentage confident, right? Because you're building a 95% confidence interval, 90% confidence interval, that kind of thing. And so whatever it is, the interval from blank to blank, which of course is your lower to your upper, captures. That's an important word, because there's this idea, this underlying idea that the population proportion, right? That's what we're trying to capture. We don't know what it is, but if I were to collect the entire population and I calculated the population proportion, it would just be one number and it's just fixed. I just don't know what it is, right? So then what I'm doing is I'm building intervals around my sample proportion, right? Building out some buffers. And then I'm trying to see if I can capture the population proportion. But I'm only 95% confident that I have, or I'm only 90% confident that I have. And so it captures the parameter. Now, in our case, the parameter of interest, that's not very telling, right? This changes the parameter of interest. So for one sample proportions, for one sample proportion questions, it is the population proportion. So for our questions, we would say we're 95%, let's say. I'll throw in 95 just to fill the blank. We're 95% confident that the interval from here to here captures the population proportion. And then it's nice to throw in what it is from the question, but you're just going to copy that from the question, right? Because the question will say, construct a 90% confidence interval for, ugh. And then you just take that, grab it, reword it as a fancy answer, then you're done. Okay. How's that for the end of a review? Yikes. That's good though. We're going to build on confidence intervals a lot, right? So eventually all this stuff is going to get, well, it's exciting because then you'll be ready for new different types of questions, right? But here we're just learning, we're laying all the groundwork, and there's a lot going on. We'll do an example. But first, I just want to plug through these kind of theoretical slides before we do. Any questions though? No. Okay. So the 95% confident, right? And I'll kind of zip through these, is really is this theoretical underlay of, okay, if I did repeated sampling, I would expect 95% of my intervals to capture the population proportion. Okay. And so what this looks like, oh, well, I guess we did talk about it. There's a cartoon, so I'm not going to skip through that. Never, if we want to be more certain that we capture the population parameter, right, increase our confidence level, then we would have to use a wider interval, right? We had that example where I tell you, okay, it's 4 kilometers to my house plus or minus 100 kilometers. You would say, oh, that's okay. How sure are you? I'm 100% certain. Not very useful, right? And so there's this trade-off between precision and confidence. And so taking a look at tomorrow's weather, the high temperature will be between 40 below zero and 200 above. This guy's never wrong. So not very informative, but confident. It's very confident. I'll keep this slide on here, but we've actually already talked about the Z star changing the width of the confidence interval, and that's really all it's doing. Yeah. How about this? I'll throw in they've only got 2 decimal places, but that's okay. If we want to make a 98% confidence interval, and I'm only going to make you do confidence intervals that are on here. So 98%, then I want a Z star of 2.326. For a 98% confidence interval. So I guess C, but option F, yay, to 3 decimal places. There's a different table that only has 2 decimal places. I just didn't catch it. But we get 3. Okay. We have already talked about that, so I don't want to do that. Here's the one that I'm going for. Okay, so just looking at here. If I know what my population proportion is, right, at this dotted line here, that's on some number line, my population proportion is fixed, okay, then what can happen? All of these are p hats. P hat, right? Our sample proportions are not exactly going to be the same as the population proportion, but we expect them to be hovering around the population proportion, right? And so all of these little dots, they're all sample proportions. Then we built a 95% confidence interval. So we go down some margin of error and some up some margin of error. But notice here that P is captured in this interval, right? Captured in all the intervals, right? Even though P hat is going to kind of scoot around, jump around, jump around, jump around. But then there's some chance that you end up with this weird anomaly of a sample proportion. Now, the reason we can only be 95% confident is because you don't know. You don't know if you're this one weird sample that you could have drawn, right? And so here, this could be a perfectly representative sample of the population. There's nothing weird about it. It's just the way the distribution of the sample proportions work. There's a chance that you have this sample, and that's why you can only be 95% confident in your interval, right? Because one of these 25, so 95%, or 5% rather, didn't capture the population proportion. And so that's going to be, so here, this is, P is the population proportion. And in this case, it is not capturing it, right? And so that's where the 95% confidence comes from. Tried to find a question to use, but instead, I'll just make one up. Let's do an example, start to finish. A random sample, nice. That's a good start. A random sample of 600 dentists found that, obviously I am making these numbers up as I go, found that 450 recommend Colgate, or should we do Crest? Doesn't matter. They all seem to have the same proportions, kind of weird. Recommend, is there 2 M's in recommend? Or is there 2 C's or both? 2 M's, 1 C. I'm just waiting for the underline, which I guess is coming. It'll like underline your typos even if you're writing. Pretty cool. I can't wait. I want it to just fix it for me. I recommend Colgate. Toothpaste, obviously. Fine. Construct a 90% confidence interval. Construct a 90% confidence interval for the proportion of dentists who recommend Colgate. We don't need, so what I love about proportion questions is we don't need very much information here, right, in order to answer the question. What do we have? Well, actually, maybe I'll pause it and give you a moment to work through it. Check your conditions. Uh-oh. Find the confidence interval and interpret the confidence interval. I'll pause the recording so it's not just a bunch of dead air. But we'll take 5 minutes. Play, good. Okay. All right. First kind of chunk of work is we have to check the conditions. What I will start doing is part of checking the conditions will be identifying if you're making a confidence interval or a hypothesis test, which we haven't done yet. So for now, just a confidence interval, but I'll write confidence interval kind of in brackets to remind myself. Yeah. Just because it will be different, slightly different, ever so slightly. Okay. Should I show you the bare minimum that you would do? Let's do it. Random, check, because it says n less than 10%. Yes. 600 is less than 10% of all dentists. I'll say reasonably. Remember, you always want to argue that all these conditions are met. So I don't know how many dentists there are. I don't really care. I'm gonna assume, I guess, that it's less than 10%, right? So even this, even if you just did n less than 10%, I'd be fine with that. Okay. This, what you don't need to say is you don't need to group it and say that this is the independence condition. I have been, just to highlight that, okay, the independence conditions, these are them. But we do need n times p hat, which is x, which is the number of successes. X is 450. I guess I should highlight. N is 600, right? My sample size is 600, and I found 450 of those recommend Colgate, so they are considered successes. So X in this case is 450. What's another way I could have written this question? I could have written it the way that we had it last day, right? A random sample of 600 dentists found that 75% of them recommend Colgate, right? So then I give you the p hat, and then you have to solve for the number of successes, right? Or I give you the number of successes and n, and you have to solve for p hat, right? But as long as you have 2 out of the 3, ain't bad. 450 is greater than or equal to 10, check mark. N times q hat, which is really n minus x, is 600 minus 450, which I'm going to go for 150. Yep, is greater than or equal to 10. Therefore, the conditions are satisfied. Therefore, the conditions are satisfied or met, if you prefer. That just means we can keep going with the question. If you were to tell me that the conditions are not satisfied, then technically you can't answer the rest of the question, and that would be bad. I'm not going to do that. This was the normality condition, but you don't need to call it by name, but you do need to check all those, right? I find it's helpful to group them like this, but if you don't, you can skip it. Okay? So pretty bare bones stuff for the conditions. Okay. Now for the work, I'll construct the confidence interval. We wanted a 90% confidence interval, which means that from our table, let's see if I can still, yeah, I have it. From the table, Z star is 1.645. Okay. The confidence interval is p hat plus minus Z star times the square root of p hat q hat over n. I didn't do that very nice, did I? That means we need p hat. You probably did it already. I'll sneak it in up here. P hat, if you have just the number of successes and the sample size, then of course your p hat is x over n, which in this case is 450 over 600. I'm going to convert this to a decimal. And if you get a lot of decimal places, keeping 4 should be safe, right? What's another thing about proportions? Proportions, probabilities have to be between 0 and 1, right? And so if you had kind of your x and your n mixed up, then you'd get something bigger than 1, and that would be bad, right? So that's your kind of stopping point to regroup. But we have a p hat of 0.75. Okay. So 75% of dentists, 75% of those 600, right? All right. So 0.75 is our best guess at what the population proportion is. But remember that graphic, right? It's going to be hovering around the population proportion, but not necessarily at the population proportion. And so then Z star is 1.645 from the table. All right. Try to keep it on one page here briefly. Okay. So far, so good. And then I'll write it nice and big here. P hat is 0.75 and Q hat is 1 minus 0.75 divided by n, which is 600. Common mistake there is using the 450, but you want to use your total sample size, right? All right. So working our way out from the inside, we're going to do the multiplication and then the division and then the square root and then multiply by 1.645. You don't need to show all those steps, but I do want to see the final margin of error before you go through and do it, okay? And so kind of optional steps are coming up here. Optional work. I want to show all the steps because then you can follow along and see the steps that I followed, but 1.645, 0.75 times 0.25 is 0.1875. divided by 600. 0.1875 divided by 600 is itty bitty 1.645. I will say, if you have, I think what happened to a number of people on the test is maybe your calculator is showing scientific notation and you're just not reading to the end, right? Because mine is showing up in scientific notation, but you should get 0.0003125. Right, so make sure that that's what you get when you do that calculation on your calculator. Let me check. 1, 2, 3, 4 times 10 to the negative 4 is what's showing up on my end. So just make sure. Then I take the square root of that little guy. So I get 0.75 plus minus 1.645 times 0.01767766953. No rounding. You can stop writing after maybe 4 decimal places as appropriate. You wouldn't want to stop after 4 decimal places here. You want to capture as much activity as you can, right? But here you've kind of caught all the action by 4 or 5 decimal places, but I want you to keep all those decimal places in your calculator. Yeah. Like I said, a lot of calculators have a store function, which I can help you find by Googling it with you, or you can just Google it yourself. Now I can times it by 1.645. This is no longer optional. 0.75 plus minus 0.02907976638. That's your margin of error. All right. I'll define it, margin of error. Sometimes it's ME or some textbooks use MOE, margin of error. I don't believe the O should be in the, what is it, acronym? No. Of, can't include of. But that's personal preference. Okay. Thinking about these, this is now a proportion, right? 0.75 is a proportion plus minus a proportion, so 2.9%, right? 75 plus minus 2.9% is how you can think about it. Okay, you can round this to, let's say, 4 decimal places, right? If I go 1, 2, 3, and then make this a 1, I've caught all the activity that I need here, right? So that's going to take some practice, just kind of knowing when you can stop writing. But if you want to play it safe, just never stop writing. Always write all the numbers. It's easy. To 4 decimal places. Okay. Finally, our interval, right, is 0.75 down 0.0291, but then also up 0.0291. So 0.75 minus 0.0291 is 0.7209 up to 0.75 plus 0.0291, 0.7791. Ooh, phase 2 complete. Phase 3, interpret the interval. What color haven't I used? I used light blue for the conditions. I used green. Okay. How about this? I'll do pink because it's the one everyone loves to forget. And it makes me so sad when I'm marking because it'll just be blank. So pink means it's important. Interpret the interval. I do make it a part of the question, right? A, check the conditions. B, construct the confidence interval. C, interpret the interval. Right? So I do kind of force you to do it. Okay. We made a 90% confidence interval. So we are 90% confident the interval from 0.7209 to 0.7791 captures, right? That's an important word. Captures what? Captures the population proportion, but not just the population proportion of dentists who recommend Colgate. Captures the population proportion of dentists who recommend Colgate. Oof. Okay. Now, a lot of the time, we prefer to talk about proportions as percentages. I do want you to be really aware, if you give the proportion here, you have to say a proportion here, right? Whereas if you gave the percentage, which you're allowed to do, then you have to change your wording to be percentage, right? And so here, I'm going to copy this. Copy. And maybe I'll make this a different color style. What color can I do? I'll do orange. Orangey glad. Or we can use percentages. But this becomes 72.09 and this becomes 77.91, captures the population percentage. Now, because the question is going to likely be about the proportion, right? I would probably recommend, crest, no. I would probably recommend just keeping it as a proportion because you'd have to do some extra thinking and make sure that what you're saying is true if you were to change it. But if you really want to do the percentage, then just make sure that you change it in both locations. Oh. This is the part that's the most important to me. I don't care if you can do the math. I don't really, I mean, I care, but that's not, the point of this course is not algebraic skills, although it helps. Right? I expect you to be able to do some math, but that's not the hard part of this course. The hard part of the course is interpreting these results. What does this mean? Okay. And so this is what is most important to me and overall in stats. Okay. Anyone can do the math, but the interpretations are hard. Okay. Any questions about that one? This is where I find out I have a typo somewhere really early on in my work. Did you mean to have a 2 there? Oh boy. No. Maybe you're just not calling me out on it. It's okay. All right. We can do confidence intervals. That's awesome. So now we're ready. I think we're ready to move into hypothesis testing. There's a couple more things I want to say, but I'll let them come up organically, I guess. I'll fill in the gaps. So section 5.3 is hypothesis testing for one sample proportion. And so here, hypothesis testing, I will abbreviate HT. Now, hypothesis testing is just as formal as it sounds, okay? And it really is kind of the backbone of statistics. And so hypothesis testing is a formal method, I'll call it. A formal method of establishing significance So significance is not a word that we're going to use lightly anymore. In fact, I have a hard time just in general, but because significance means in the statistical sense, right? Statistical significance. Statistical significance requires hypothesis testing. So in order for someone to say, for example, this, how about my class average was significantly higher than the other class average? How about that? So for example, my class average was significantly higher than the other class average. We are the only Stat 121, so it doesn't really work, but there's Stat 124s. It's the same, right? In order to be able to say significantly higher, we would need a hypothesis test to do that. Yeah. One of the main concerns that I have whenever I do multiple versions is I have to make sure that there's not a significant difference in the grades between the versions. That would be really bad, right? And so I always do a hypothesis test to make sure that they're not significantly different, right? They can be, they won't be exactly the same, but because of variability, right, we know that, okay, they're basically the same, right? And so that's what the hypothesis test does for us. It's going to take us a while to be able to compare two means, right? The average on one test version versus the average on another test version, but we will be able to do that. Okay? And so, but you'll have to wait many sections until then, okay? But we will be able to. For now, for one sample proportion, and you know what? I am going to add a page. Got a lot to say. For one sample proportion questions, remember I classify all of these by types. So this is the type. We have only introduced one type of question. Right? But for one sample proportion questions, right, I'm going to have some sample proportion, of course, and I want to compare it to some number. In fact, I want to compare it to some stated proportion. So for one sample proportion questions, we compare our sample proportion p hat to a hypothesized proportion. To a hypothesized proportion, which we're going to denote by p subscript 0, which is new. So some new notation. It's still a proportion. Proportions still have to be between 0 and 1. All the same rules apply. But now I have this number that I want to compare my sample proportion to. Right? And so the hypothesized proportion, P naught, is a number between 0 and 1 because it's a proportion. Now it's going to come from the question. From the question. That's probably the hard part, because sometimes this hypothesized proportion, or the number that you want to compare your sample proportion to, right, is kind of hard to find. Okay? One of the main ones that always kind of wreaks havoc is if I say the majority. What does that mean in terms of a proportion? A majority means more than 50%, right? And so then really what I'm saying is that what I want to compare my sample proportion to is 50%. Is it 50% or higher, right? And so that's kind of the one of the majority is more than 50%. And I always get questions because there's a couple of assignment questions where it says, is there evidence that a majority of voters will vote for this candidate, right? How do I know? Just need to take a step back. You know what majority means. You just maybe haven't thought of it as a proportion. But so then P naught must be 0.5, right? This is a 0. And I am saying P naught, but it's really P subscript 0. I'm holding off. I'm telling you why for just a little moment longer. And so one of the main things is majority throws people off, but then just as long as you remember, okay, then my benchmark that I want to compare my sample proportion to is going to be 50% or 0.5, of course, because it has to be a proportion. Okay. Good. Should we I'm at a crossroads. Should I go rogue? we can just talk our way through this thing. There's slides, but I didn't rearrange them. I don't like the order. So I'm gonna insert a lot of pages. How about this? First things first, the conditions, we can start there, is basically the same for a hypothesis test and a confidence interval. Now I know I haven't said really what a hypothesis test or what it entails or anything like that. And that's on purpose. So we'll start with the conditions, something that we know. Let's see here. So the conditions for a hypothesis test are these. The first two conditions are the same. That's nice. Kind of less memory space, right? So we have to have a random sample. And we still have the n less than 10% condition. So your sample size has to be less than 10% of the population. And this I'll summarize as the independence condition. Now, what's new for the normality condition is that, okay, normality for a hypothesis test is going to be n times p naught. That's different, right? This is the number of successes I would expect to see if the null hypothesis is true. Too many words. But for now, we just need n times p naught. So this is, notice the difference here, has to be greater than or equal to 10. At least 10 expected successes. For the confidence interval, it was observed, but for a hypothesis test, it's the expected. N times Q naught, where, you know, Q naught is 1 minus P naught, of course. Also has to be greater than or equal to 10, which means I need at least 10 expected failures. Which means that before you do any hypothesis testing, you still have to have an idea of what your P naught is, the value that you want to compare your sample proportion to. Besides that, all of these, this looks familiar still, right? Just changed one little thing. And like I said, these will always pass. It's not that, it's just you need to know to check them. Okay. If the conditions are satisfied, we can proceed with the hypothesis test. What is it, Emily? I know, and you won't believe what happens next. This whole class is clickbait, I guess. How about we start by looking at the formula sheet? Let's do that. So I'm going to grab from our formula sheet. Where is it? one sample proportion, we've done the confidence interval. Hey, look at this, a hypothesis test for the population proportion P. Let's grab that. Copy. There's a lot of things on here that we don't know. That's okay. We're gonna pick away at them. But there are a lot of things on here that we do know, right? And so first things first, hey, Z, I know how to work with Zs, right? Zs are on a normal distribution centered on 0 with a standard deviation of 1. I know how to find probabilities associated with a Z, right? Because we did it just on the test, right? And so we use the table. And so we know a lot about Z already, okay? We know what P hat is. Remember what Z did before? Z, just as a little side note here, we used Z as X minus mu over sigma. But what did we really say? We said, okay, what we want to know is how many standard deviations is X from mu, right? Now, if we apply this to this mess over here, really all we're saying is, okay, how many standard errors? This is going to be your standard error. Standard error of P hat has changed just slightly. P naught Q naught over N, right? Just changed by those. Whereas in the confidence interval, we use the P hat Q hat. I use this to remind myself which ones to use in my conditions that I have to check, right? It's whatever ones I used in my conditions. Right? So here, same as conditions for a hypothesis test. Now, the reason we use the hypothesized proportion is because now I have this underlying idea of what I want to compare my sample proportion to. So I have this hypothesized population proportion in mind. Okay? And so really this is saying, and we are going to pick this apart more, but H subscript 0 is called the null hypothesis. And it is going to be my hypothesized. If I say hypothesized, I'm assuming that you've all kind of touched on the term at some point. I remember in, I want to say grade 9 science, we had to state a hypothesis. My hypothesis for my project was that there was more pollution alongside the highways than on rural roads. Sure, hard to test, I guess. Things like that, right? We've got this idea, and then we go out and we test it, and then we draw a conclusion. And so this is going to be my hypothesized population proportion in this case, because we're doing a hypothesis test for P. And I'll come back to the null hypothesis, but now, okay, I need some baseline. So now I use the P naught because I have some hypothesized proportion for my population, which should be better than my sample proportion, than just reusing my sample proportion. So this changes a little bit, but it is still the standard error. It's just we've improved our guess at what P is. In fact, we're relying on our hypothesis. Okay, and then P naught, P subscript 0, although I haven't fixed it on this one. This is actually an O for some reason. It's not a 0. It should be a 0. That's a typo. But it's so hard to tell. I never caught it until another prof was using my formula sheet last year. She goes, I think this is an O. How could you see that? I don't know, but she was right. Okay, so credit where credit's due. I made a typo. All right, so really what this Z, we calculate Z to find how many standard errors right? P hat is, or our sample proportion, I'll write it up properly. Our sample proportion, P hat, is from the hypothesized proportion. P naught. What this is going to look like is, if the conditions are met, we can assume a normal distribution. We also assume that it is centered on P naught until potentially we have proof otherwise. So then what we're going to find is that if I find that my sample proportion is out here somewhere, I can calculate the Z, right? How many standard errors away from the center is this thing? But there's going to be a region here where we consider them essentially the same, right? And so then our null hypothesis that P is equal to P naught is perfectly fine. Yeah? But there's going to come a point where if you think about, okay, so I'll stand here, right? Here, you would say, oh, Emily's standing over there by the desk, right? Or like the lectern or whatever we're calling this thing, right? Even though I'm not right at it, I'm over here, right? Even if I move over here, it's totally fine, right? I can kind of move around, but then there's some point where internally, maybe over here, you would stop saying that, oh, she's over there by the lectern or whatever this thing's called, right? And you would maybe say, oh, she's over there by the screen, or oh, she's over there by the whiteboard or whatever, right? But we have this internal stopping point where you would stop saying that I'm basically over here by this thing, right? And so what we have is we have these kind of invisible bounds where P hat is not significantly different from P naught, right? Somewhere in this region. We're going to quantify that region, of course, but that's the idea, right? So whereas if I found another, let's call this P hat 1 from my first sample, what if I found a different sample? I found that this P hat The second p hat was way out in the tails, right? So many standard errors away from p naught. Then I would say, okay, it's unlikely, but still possible, right? Because there's area in the tail, so it's still possible that it came from a distribution centered on p naught, but it's unlikely, right? So that's why I'm going to reject this hypothesis that p is centered on p naught and probably centered on something else. Okay. So this idea out here, let's see here. Anything out in this region, p hat is significantly different from p naught. But that can happen in the other tail, bless you, is significantly different from p naught, regardless of which direction we're going in. Okay. That's going to be the underlying idea of hypothesis testing, is this idea that, okay, at some point, my sample proportion is too far away from my hypothesized proportion to have come from that distribution reasonably. Okay. And so we have a quick guide for what that distance should be, right? We've been using p naught plus 2 times the standard error, right? So z plus z is 2. Right? Or down 2 standard errors, p naught minus 2 standard errors, which means that z is -2. So just as a quick guide, if it's more than 2 standard errors away, right, then what does that link to? 2 standard errors, 95%, right, from the 68, 95, 99.7 rule. So as long as you've passed 2 standard errors, so a z of 2 plus or minus 2 in either direction, right, then it's likely that we're going to reject the null hypothesis. So here, if z is greater than plus minus 2, obviously -2, kind of less than -2, but kind of beyond -2. I'll say not greater than, because that's technically incorrect. Beyond plus minus 2. We usually reject the null hypothesis You're going to reject it, you should probably have an alternative hypothesis lined up, and we will, right? But we're just establishing the overall idea. Now, we could talk about Zs, right? But it's really hard to communicate to your boss, for example, or to the general public. Well, I mean, we found something that was 4 standard errors above the hypothesized proportion, and people just kind of glaze over. What's a better way to communicate that? We can communicate that with probabilities, right? The probability of seeing this, if the null hypothesis is true, is this number, right? And we have this kind of innate ability as humans to understand probabilities relatively well. Okay, and so in hypothesis testing, we don't communicate our results in terms of Z, right? We communicate them in terms of probabilities. Remember, this is the moneymaker of statistics. And so they want to be spoon-fed all this information. You can't make them learn about Z scores and stuff. Okay. And so in hypothesis testing, we don't communicate results in terms of Z scores, even though we could, right? Technically, they're there. Instead, we use probabilities. Really only one probability. Probabilities okay, I regret that underline, but I'm going to probabilities. It's only one, so how about I make it singular? We use a probability, sorry, called a p-value. That gets kind of tricky because we have p's for sample or p-hats for sample proportions, we have p's for population proportions, we have p-naughts for hypothesized proportions, and now we introduce a p-value, and it's our job to keep them all straight. They're all different, distinct things, so we need to just keep a handle on these guys. Now the p-value is going to be very important, but it's also one of the hardest things to grasp in this course. Okay, and so if it doesn't sink in right away, that's totally normal. In fact, I'll confess right now, it wasn't until I was studying for my final exam in my first stats course that I was like, oh, I see, eureka. And maybe that's embarrassing, but I've taught it long enough to know that that's not embarrassing. It's totally normal. And so for now, we just need to memorize what it is. I know it's a total bummer, but what is the p-value? The p-value is going to be the probability, because it is a probability, the probability of seeing, I'll do it specific to this one sample proportion type of question because we're just starting. And then later on, when we're ready, I'll introduce the general form. But the probability of seeing a sample proportion p hat as extreme or more extreme page as what we saw, assuming the null hypothesis is true. Assuming the null hypothesis is true. So if we take this the null hypothesis, and I'll add in what that's going to be. In this case, that P is equal to P naught is true. Yeah. So if the population proportion is in fact centered on, or is in fact this number that we've drawn up, right, from the question, then the probability of seeing our p hat should be quite high, right? It should be hovering around the center. And so what's this going to translate to in terms of our curve? So here, if it's centered on P naught, right, and we found a P hat that's up here, for example, then the probability is an area under the curve, right? We know that. How do I get that area under the curve? Well, I calculate a z-score, right? And so the probability or the area under the curve of seeing a sample proportion p hat as extreme or more extreme, right? That means the area in the tail, right? And so as extreme or more extreme, this is the one-tailed p-value. Now we've seen one-sided p on our table already, right? And this is where the two-sided p comes into play. And so here, this is the one-sided, oops, p, which is really the p-value. And maybe I'll call it the p-value. I'll switch these around, sorry. P on the table. They didn't write p-value, they just wrote p. Now, depending on what we're interested in, it's possible, and let's see if I can change this. This could have just as well happened on the other end. So there are times where maybe we're interested in both these tail areas. Then the two of these would be the two-sided P. Two-sided p-values, or p-value singular. Yeah. We'll just sit on that for a little bit. Okay. Our sample proportion's only going to happen in one of the tails, but from here, from this definition, right, as extreme or more extreme means into the tails, regardless of which side you were on, right? And so it's always into the tails. And this part, assuming that the null hypothesis is true, that's what lets us center it on P naught, right? Because we need some anchor. Okay. Oh, I don't want this pen anymore. There. So instead of talking about if Z is beyond plus minus 2, what we're going to do is we're going to talk about the probabilities. But at Z plus minus 2, right, how much area do I have in the tails? I have, well, if I'm got 95% in the center, then I have 5% split between the two tails, right? So 2.5, 2.5, right? And so here, for our Z is centered on 0. And if I'm at -2 and +2, then I have roughly 95% between there. And I have 2.5%, and I have 2.5%. So then the possible area in the tails, so the total area in the tails is 5% or 0.05. That's going to be our defaults. Default what? If the area in the tail, so if the p-value is small enough, we have enough evidence to reject H0. If the p-value is small enough, we have enough evidence to reject H0. That's the same idea, right? Over here, P hat is basically the same as P0, blah, blah, blah. I'm standing over here at the desk, and then I move further and further and further away in either direction, right? And at some point you stop saying, oh, they're basically the same, right? And so we need some guideline. And so usually small enough, the default is 0.05. This is what we call an alpha level, but I think it's too late in the class to introduce another term. So small enough, if it's less than, and maybe I'll add that, default is less than 0.05. Change that. Then we have enough evidence to reject H0. Yeah. I'll let you stew on that over the weekend, and then we'll start with some more theory on Tuesday. I hope you have a great weekend, and I'll see you on Tuesday.